All right, so let's get going. So how'd the assignment go? Easy? My my feeling is that this should have probably been, for most of you, the most frustrating assignment you've had so far with the uh between last semester. Well, this semester's new, but um merge sort is just difficult to wrap your mind around. And the reason why we cover it, you'll actually see it every single year during your 4 years here. Um, and the hope is by the time you see it in the language theory class as a senior, where one of the early assignments is merge sort, it'll finally kind of have clicked. Because once merge sort, I don't know, it's like an example of an algorithm that once you can conceptualize the whole thing, you're pretty much set as a computer scientist. I would say that's one of the evidences. So if this was a struggle for you, don't be too concerned. It was probably a struggle for most people. But I mean, it's still a zero if it didn't work perfectly. So it's you got that going for you. All right. So assignment. Do I have you write the whole thing or just up to the merge step? I know we covered the whole thing, right? Whole thing? Okay, so let's go. And I think I did give you some hints though here, right? I think at some point I told you the oh, well, you can go back to the video, right? Didn't I say go back and watch the yeah, because I think I told you how to find the midpoint, begin plus end divided by 2. And then that's one midpoint, and then that plus 1 gets you to the next thing. So those are typically the sticking points for merge sort. All right, so let's look at this guy. And just as a reminder, this Friday will be the same as last Friday, so we'll be on Zoom only. I have they're doing the left side of my back early morning Friday, and then I should be done for a while, is the theory. All right, so did I give you a starting point? All right, so here in Maine, we've created an array with 11 elements in it. I think as a starting example, I wanted you to have an odd number of things. The algorithm will work for even or odd, but typically if you do it for odd number first, then you prove to yourself your midpoint logic is correct. So put 11 elements in it. I showed you how to get the random number generator in Java. It's inside of java.util.random. We went through every element of our array, and we got the max, the absolute value of the next integer, which is the range of all integers. So negative 2.1 billion to positive 2.1 billion. That's what r.nextint gives you. It gives you a random integer in the range of all integers. So then I'm modding that by 50 and taking the absolute value of it, which will give me a positive number between 0 and 49. All right. So we're filling up our array with random numbers between 0 and 49. I wrote a function called display here, which just takes in an array, goes through and displays it all on one line, and then kicks it down a line at the end. So the idea here for your homework is you would display the unsorted array, then call merge sort, then display the array again, and it should now be in order. Okay. Right now, though, it's going to be the same array twice, because merge sort currently doesn't have any logic in it. We're calling it, and it does nothing to your data, and we move on with life. All right, so now let's go ahead and write merge sort. Remember, merge sort operates on this idea of a list being trivially sorted. That is that the begin and end are the same value, same position. So if the portion of our array that we're looking at is only one element big, by definition, that is sorted. Make sense? All right, so right at the beginning of merge sort, we're going to say if begin is not equal to end, then we need to call merge sort on the left half and right half. Okay. So that's what we do over and over and over again. We call merge sort in the left half and the right half if we don't have a one list. Once we're guaranteed to have a one list, once we are here, that is either after our two calls the merge sort have completed, or we are finally down into an endpoint. We want to go ahead and merge. Now, we know that if begin and end are equal to each other, so if begin is equivalent to end, we know that this list is sorted, correct? And if this list is sorted, we don't have to do anything. There's no merging, there's no whatever. Okay, so we're only going to do something inside of this function if begin and end are not equal. Okay, so we need to figure out where our begin and where our end is for the left half and for the right half. So we're going to have four variables. So int begin one, int begin, well, let's just do end one next. Int begin two, int end two. So two of these we could fill out real quickly. The beginning position in the left half will be equal to whatever begin is. And the ending position of the right half will be whatever end currently is. Those two guys in the middle, that are the tricky points here. So end one is going to be begin plus end divided by 2. So whatever begin plus end is divided by 2 will give us the index of the middle of our list. All right. Begin 2 is end 1 plus 1. Is 1 bigger than that? All right, makes some sense so far? All right, so those four variables are kind of the magic here, really, with the emphasis being on getting that midpoint. All right, so now we know where the beginning and ending of the first half is, and we know where the beginning and the ending of the second half is. Notice that merge sort does not return a value. Yet, the presumption is that inside of merge sort, we're going to be doing that merge step where we're moving stuff around inside of the arrays. Why don't we have to return a value? Why are we confident that our array AR is going to be changing as we call through merge sort when we're not actually returning a new version of AR? Go ahead. It starts off as random values, but how do we know why it's not changing? Go ahead. Yeah, so we are passing the memory address of this array. So any work we do on this array, any manipulation is happening to the original, not a copy of it. All right. That's why we don't have to return that value as we're going through here, because we have this constantly changing location in memory. We're working with the single array, not copies of it. We're working with different portions of that array. Every time we call merge sort, we're saying only look at that array from position begin to position end, from position begin to position end. So we're looking at subsets of the array, but we still have access to the entire array. All right, so the first thing we're going to do is call merge sort, passing it the entire array, passing it begin one, and passing it end one. That's calling merge sort on the first half. Then we're going to call merge sort on the second half, passing it the entire array, begin to, end to. So the beginning and ending of the second half of it. Make sense? All right. So we're going to keep doing that over and over and over again until we get to one lists. And then once we pop up after we found a one list, we are here once we know that AR is sorted between begin one and end one, as well as begin to and end to. So after those two calls to merge sort, after they finally return, when we get to this line of code right here, we know that the first half is sorted. It might just be a one list that we didn't actually make any changes to, and it's just sorted because there's only one element. Or it's sorted because maybe we had three things, but we've already done that merge step to merge them back together. So one way or another, we know that our array is sorted between begin one and end one, and we know that it's also sorted between begin two and end two. So our next step would be to go ahead and give ourselves a temporary array so that we can do that merge step and then copy the values back over. Okay? So how big of an array do we need here? If originally my array had 11 elements in it, okay, let's just use that as our starting point, and 11 elements in it, and I passed in 0 to the length minus 1, 0 to 10. How do I get the number of elements that are in that array between the begin and end that we're currently looking at? So I originally said I created an array with 11 elements. When I made my first single call to merge sort, this is the guy that gets the ball rolling. Okay, I said, here's my array, start at bucket 0, go all the way to the last legal bucket in it. So I would have passed it a 10 in this case, but there are 11 elements. So how do I get the length of that array? The length of the portion of that array I'm dealing with. Go ahead. N minus begin plus 1. So I'm going to go ahead and create a new array. So I'm going to say int array temp is equal to a new int array of end minus begin plus 1. So if we think about this as our original call to merge sort, if I passed in a 0 and I passed in a 10, 10 minus 0 is 0 plus 1 is, or 10 minus 0 is 10 plus 1 is 11. There are 11 elements in this list that I need to place. Okay. Now we already know where the begin and end of this guy is. We know that the beginning of the first half is at begin 1 and the beginning of the second half is at begin 2. Now we can use those values if we want and just modify begin 1 and begin 2. But I think when I did the example, I gave you some new variables like pause 1, pause 2 for stepping through. All right, so we're going to go ahead and say int pause 1 is equal to begin 1. I'm going to put a little comment out here. This keeps track of where we are on the left half. Then int pause 2 is going to be equal to begin 2. Oh, Ninja. Keeps track of where we are in the right half. All right. Because remember, we're basically comparing whatever pause 1 is pointing to and whatever pause 2 is pointing to and picking the smallest of those values and putting it into our temp. Do that. N minus begin plus 1 times, and then copy your values, your now sorted values back over. Okay. So I know I'm going to need to do something some number of times. So I'll say for int I is equal to 0, I is less than temp dot length I plus plus. However many elements are in my temporary array, that's the number of winners I'm going to have to place. Okay. So now I have 3 different possibilities here. if both pos 1 and pos 2 are currently pointing to legal positions in their halves, their respective halves, that is that pos 1 is less than or equal to n1, and pos 2 is less than or equal to n2. If both of those statements are true, that means we actually do have two values that we want to compare to each other to see who wins, who gets to go into the next bucket I of my temp array. So if pos 1 is less than or equal to n1 and pos 2 is less than or equal to n2, if both of those things are true, we can put a little comment here saying that pos 1 and pos 2 are legal positions. Then I want to ask the question, which value in AR at position pos 1 or at position pos 2 is the smaller value? If AR at bucket pos 1 is less than AR at bucket pos 2, that means AR at bucket pos 1 was our winner. So we're going to go ahead and place that. So temp at bucket I is equal to AR at pos 1. And then we'll say pos 1 plus plus. So if the element at bucket pos 1 is smaller than the element at bucket pos 2, I'll pick pos 1 as the winner, the element at bucket pos 1, store it in my temporary array at the next spot, and then increment pos 1 because we've already placed that guy as a winner. So the next time through, pos 1 now points to a different place in the array, and pos 2 points to the place that lost last time to see if he can be a winner soon. All right. The else to this guy. So if the element at pos 1 is not less than the element at pos 2, then that means the element at pos 2 must be smaller or potentially equal. And if it's equal, it doesn't matter which of the two we grab. So we would say temp at bucket I gets the value of AR at bucket pos 2 plus plus. Make sense? All right. But that's only if they're both legal. We only have to compare them to each other if pos 1 and pos 2 are both still pointing to something in their respective halves of the list. Else if they're not both legal, that means at least one of them is not legal. We're still in this loop. We know exactly one of them is not legal because this loop goes through the exact number of times that we need to pick winners. Make sense? So else if pos 1 is less than or equal to n1. So this says, is pos 1 the legal position? That's what that asks. If pos 1 is the legal position, then what do? We go ahead and record. We just assume that the element at position pos 1 is the winner. Add it to our next bucket of temp, increment pos 1. Else is pos 2 the legal position? That's what this guy means. If I'm in this else, then I want to say temp at bucket pos 2 gets placed in my temp array and increment pos 2. Now, this is starting to stretch out a little bit. It feels like we're saying a lot of stuff, but we're actually just asking a couple of questions. We're saying I need to find temp.length number of winners to put into my temp array. I'm going to try to compare the element in my first half to the element in my second half as long as I can. So if both of them are legal positions, I'm going to say if the first one is smaller than the second one, place the first one inside of my temp array. Otherwise, place the second one inside of my temp array, making sure we update the count. Keep track of where we've already placed. Otherwise, if they're not both legal, one of them must be illegal. So is pause one legal? If it is, if pause one is still pointing to somewhere on the left list, we'll just go ahead and accept pause one as our default winner and increment pause one. Otherwise, we'll accept pause two as our default winner and increment pause two. So when we get right here, temp is filled with the elements from the first half and second half in order. That's what we're dealing with when we get to that line right now. It has not been copied back over to the original array. A couple minutes ago, I asked, why didn't we have to return values? Because we're dealing with the pointer to the original array. Right now, I have my values that are in order inside of temp. I need to now copy them back over to my original array. Now, where in my original array am I going to be copying? I'm going to be copying between begin one and end two. Or I could think of it as begin and end. Where int I is equal to begin, I is less than or equal to end, because end keeps track of the last legal position we're interested in our merge sort. All right. Kind of another important caveat of some algorithms. You need to make sure that when you're dealing with the beginning and ending of something, know what those mean. A lot of times the ending part is where the question is ending inclusive or non-inclusive? All right. So in this particular case, we look right back to when we first called this, we created an array with 11 elements in it. And the legal buckets in there are buckets 0 through 10. That gives us 11 unique buckets. What we passed in for end here is bucket 10, 11 minus 1. So end is the last legal bucket inside of our array. It's an actual place. It's a place we need to deal with. That's why we say equal sign here. I is less than or equal to end. So we want to place there. I plus plus. All right. So this is the section of AR that we want to put values back into. Now, we could, inside of our for loop here, we could go ahead and create another variable for keeping track of where we are in temp. So we could say J starts off at 0, keeps going as long as it's temp less than temp.length, J++. But we can actually just go ahead and steal one of our other variables really quickly. So I can say pause 1, just reset it to 0. We've already used it. Pause 1 served its purpose. All right. So I'm going to keep track of pause 1. Actually, you know what? Just to be clear here, we're going to say temp pause starts off at 0. Where are we in the temp array? That's what we're going to put in that guy. And we certainly could have put this inside of our array here. I think the syntax is temp pause is equal to 0. And then temp pause plus plus. I think that's how you could have 2 different variables inside your loop. I would say if you start doing that, things start getting a little bit wonky, kind of a weird syntax to have to remember. So if I were writing this, I would probably just use this little throwaway variable on the outside. My function's almost done anyways. That way I can have my array here, my for loop here, focus on the aspect of AR that I care about. All right. So I'm going to put inside of AR at bucket I. So I'm copying the values from temp, back over to my original array. Where in my original array am I interested in? Between begin and end. That section of AR that was passed into this call to merge sort. All right. So I'm going to overwrite AR at bucket I with temp at bucket temp pause. And then make sure you increment temp pause. Now, let me ask you this little trivia question. Is the code I have there the same? Ooh, what did you do? That do the same thing? How many people think, yes, it does the identical thing? Anybody think it doesn't do the identical thing? Okay, let me throw another curveball. What about now? So we think it does not do the identical thing now. Why not?
Plus plus before it runs.
Okay, which means what? Plus plus temp pause. How is that different than temp pause plus plus?
Plus plus before it's getting added before it's happening.
Yep. So in this particular case, we want the current value of temp pause. That's the value we're placing into AR. And then after we get that position, we want temp pause to be incremented. All right. So what I have written right there is identical in terms of function to that, which is better. Does it still work if I do that? Yep. Because it doesn't matter whether I have the plus plus before or after if I have it on its own line. Sure, people are impressed if we know how to wield that plus plus thing and can, sneak in that little increment right there inside of our code. But that is an error prone type of thing, right? It's not a difficult thing. It's an easy enough concept to wrap your mind around. But as beginning programmers, we got enough stuff to worry about, right? So anything you can do to reduce your chances of errors, the better. So I would generally say if you're questioning whether you can do something in less lines of code, stop questioning that. Eventually that'll come naturally. You'll just say, oh, I'm just going to write it this way because you don't care who else is looking at stuff. You can get into some pretty quirky, inline if statements and stuff like that that make things even shorter, but only people who've been coding since like, I don't know, the 80s. If we use an example here, so I can say something like, that's going to be let me just do it back out in Maine to show you an example here. So I can say int age is equal to 5 if age is less than 21. Get out of the bar. Else so we can write an if statement like that, or we can do something like age less than 21 question mark. All that code there, this does the equivalent. This is called an inline if statement. Now, every now and then, an inline if statement allows you to accomplish something that you otherwise might not be able to do. A lot of times it comes down to whether or not you're using a single value. So you might, instead of printing stuff here, you might say, say something like this. So that's even a shorter way of writing it. So I'm going to print something. What am I printing? I'm printing some string. What string? Well, if age is less than 21, this guy's going to boil down to this string. Otherwise, it'll boil down to this string. And that's what I'm printing. Neat enough stuff. Now you've seen it. If you see some older code and you see something like this in there, it is handy. This is something that came from the C programming language. But isn't this just so much clearer? It only costs a couple of extra lines. So that's an inline if statement. I won't ask you about that on tests or anything. I just wanted you to see it in case you run into it looking at any examples or something like that. All right. So I would say it would always be unwise to increment temp pos inside of that thing. I would do it on its own line. Choose your poison plus temp pos plus temp pos plus equals 1, temp pos equals temp pos plus 1. All of those will do the exact same thing by making it one bigger than it used to be. All right. If you do that on its own line, then you don't worry about getting the wrong value. So what's this loop do? This loop goes through AR between begin and end, including end, and overwrites AR at that position with temp at bucket 0, then temp at bucket 1, then temp at bucket 2, so on and so forth. So we overwrite AR with our now sorted temp. All right, so at this point, our call to merge sort is done, right? So here's this if statement. If begin is not equal to end, that's the only time that merge sort does something. If begin is not equal to end. If begin and end are the same, it's sorted. We don't need to do magic. So only if they're not the same do we do something. And what do? We figure out the left half and the right half. We call merge sort in each of those. Then we do our merge step, where we step through, pick the winners between pos 1 and pos 2, and then ultimately copy the answer from temp back over into AR, the original location in AR. So once this call to merge sort is done, AR has been changed. Some subsection of AR has now been overwritten with a sorted version of it from temp. And now when another call to merge sort goes to interact with AR again, it's now working with that new sorted subsection. So if everything worked to plan here, we get our sorted merge sort. So when you see it and we walk through it little chunks at a time, it doesn't seem that bad, right? But there's like 5 little moving pieces you have to keep track of, keeping in mind that you're already intimidated by the double recursion call. That's the kicker with merge sort. That's why it's such a good educational tool. Because if single recursion didn't screw you up, double recursion will have you uncomfortable. So if there's a piece from this that I want you to really walk away with here, it's not am I good at recursion or not yet? It's the idea of we have a function that sorts an array from begin to end, whatever we say begin and end is. So you go to Home Depot and you buy this tool. Okay, so I have a tool in my hand called merge sort that I can throw it an array and the portion of the array that I want it to sort, and it does it. We don't need to think about how it does it. As computer scientists, we're interested in that. We just wrote that, yada, yada, yada. But for right now, let's think about that as just a black box. I went to Home Depot. I now have a tool that I can throw an array to, and the subsection of the array, including the entire array from 0 to the last legal bucket, and it will sort it. When I am inside the logic here, if I'm not dealing with a already default sorted array, and I want to sort the first half and the second half, I already have a tool in my hand that knows how to sort portions of an array. That black box, the thing I got from Home Depot, it's like, oh, I can just use this again. This is the positions of the left half of the array. What do I do with those? Well, I'll just call my merge sort again. Why? That guy knows how to sort portions of an array. Kind of getting out of your own way and worrying about the logic too much. We've already written the logic, or whoever wrote it and sold it at Home Depot, which would be a weird thing to sell at Home Depot, but I've seen weirder stuff. But somebody already wrote this. So now you have a tool. You say, oh, well, I need to sort the left half. How do I do that? Call merge sort. I need to sort the right half. How do I do that? Call merge sort. Merge sort sorts portions of a list. That makes sense? So when you start thinking about recursion, I want you to think about what the tools do and when do you call them? When do we call merge sort? We call merge sort whenever we need to sort a portion of a list, including the entire list if we put the portion from the beginning to the very end. All right. So that's why we're calling it recursively twice. Sort the left and sort the right. We don't necessarily care in what order those happen, as long as in the end they ultimately get sorted. Because what's ultimately going to happen here is the entire left half. If you remember from last Friday, we went through this, the entire left half of our array gets sorted first. And then we get started on the right half. And then that unfolds. So even when we make our first call and say sort the left half and sort the right half, this guy's sitting out here in limbo while we just keep going down the line here on the left half until we finally finish with that. And we're stuck with a left half that's all in order and a right half that hasn't even been touched. And then we start going down the right half line. Make some sense? All right, so we'll call that good for merge sort. Hopefully after you saw it, it wasn't that bad. As far as like exams and stuff go, recursion would be fair, but anything I ask you to do on an exam with recursion would probably be a very simple example of recursion, kind of like a factorial level type thing. You won't have to memorize the merge sort algorithm or anything like that. Like I said, this really exists as like a litmus test for you as you move through the program. You're going to find that this becomes easier and easier and easier until it's like, oh, well, that wasn't that bad. And then you start looking down on merge sort and saying, well, why would I ever use this? We talked last time about recursion in general, where recursion is memory inefficient, right? Now let me just collapse a couple of things here to make it look a little cleaner. And I know I have some comments and stuff in here. But outside of those variables, the entirety of merge sort is right here. Call it twice, do the merge step. And what's inside these for loops are simple lines of code, right? Ask a couple questions, copy something over. But in general, we want to think about recursive calls as being, we need to be careful with them. because they take up a lot of memory. Every single time we call merge sort here, we're having to put the current version of it on hold. So we can go and do with the left half, then the left half of the left half, then the left half of the left half of the left half, so on and so forth, right? And that's taking up more and more and more and more memory. Forget about the logic that's in here. At the very least, we're passing a pointer to an array. So that's whatever the size of a memory address is on that operating system. I think we saw last semester for online GDB, it uses a 48-bit memory address. 16 bits is for the system administrator special addresses, but regardless, 48 bits is how big that memory address is. So this is 48 bits plus begin one is an int, so that's 32 bits plus 32 bits, so that's 64 bits, about 112 bits, something like that. Plus a little overhead for like the name of the function and stuff like that. So call it 130 bits. Every time we make the recursive call, we have 130 bits of stuff we have to keep track of. So we have a couple of extra variables and things like that in there that we need to remember where they left off. So we're not talking about tons and tons and tons of data here, but imagine as your size of the data you're sorting gets bigger and bigger and bigger, what happens? You start taking up a lot more space. And the stuff for recursion lives on something called a stack. Okay, you'll learn about stacks in CSC300 the next course. You'll talk about stacks in CSC325 when you talk about assembly language, because you manipulate directly with the stack and the heap with that. But it's not an infinite size thing. So recursion isn't always the correct solution. Recursion doesn't mean a better solution. But sometimes if you're working with a problem that isn't necessarily computationally complex, you can write it in a cleaner way using recursion. Merge sort, if I said you have to write merge sort, but you have to implement it iteratively, can't use recursion. It would be very, very, very difficult to write. Potentially impossible. You might need to just take some caveats and make a merge sort like implementation. Merge sort lends itself to this idea of being able to call merge sort in different portions. It's a recursive algorithm. Just like some of the things we've talked about, especially last semester, there's these algorithms that are specifically quantum algorithms. Doesn't matter whether you understand them or not, they're a black box you get from Home Depot. And if you need to do a quantum type problem, you use that thing to do it and magically it works. Okay. But can you give me an example of when merge sort today might be a very, very, very good sorting algorithm, a fast sorting algorithm? And the hint here would be is a recursive call to merge sort doesn't have to necessarily mean more memory. What we described so far is how recursion would work on a computer with a single processor. A single core can only do one thing at once, where we can't be working on the left half and the right half at the same time. They got to get in line. But what if I said, hey, why don't we go ahead and have our merge sort, instead of recursively calling it on the left and recursively calling it on the right, why don't I go ahead and create two worker bees and have one of those threads deal with the left side and have the other thread deal with the right side. And then each of those has a couple of worker bees that deals with the left side and deals with the right side until they finally are done. And then they have to come back together at the top and finally do that last merge step. Make sense what I'm saying? In an example like that, where we have multiple cores in our processor. So in my example here, where I think we didn't have to make that many calls to merge sort. I think I made a total of 8 calls, maybe something like that. Let's just say that's true. Let's assume I have an 8-core processor. That means I can actually get this entire thing sorted effectively simultaneously. with the only thing blocking being the merge step at the very last step. All of a sudden, this has an 8-time speed up or a 7.5 times speed up because I'm doing it across multiple processors. It's a problem that can be subdivided. Make some sense? All right. So in order to accomplish that kind of thing, let's call this, well, we have this thing called inter-process communication. We can think of this as, for us, we are communicating between threads, so lightweight processes, because we certainly can't have, if we have 2 worker bees, we just think about it at the top level, and one worker bee is working on the left half of the list, doing merge sort in the left half, and the other worker bee is working on the right side of the list. We can't do that merge step, that final step where we merge them back together until both of those guys are done. If we do merge step before either of them are done, we're going to be merging, merge sort breaks, right? The merge sort relies on the left half and the right half being sorted in and of themselves. Okay. But if each of these threads goes and does their thing and then is able to let the guy above them know, okay, I have finished, you can now go do your step. You've gotten some speed up, but by putting the pauses in there where you absolutely have to pause, where we just think about the initial first half and the second half, if that original call to merge sort can't do the final merge step until the worker B1 and worker B2 are both done, they have to sit there and twiddle their fingers until both threads report back and say, okay, I've done my part. My side of the list is sorted. And then the original thread can then do the final merge. So we have to think about, how can threads let each other know when they have completed something? All right, so we're going to look at that on Friday. And I think that's going to basically take us to where I want to get us for Java. So then we're going to start looking at Unity. And the main reason I do this thread stuff before we jump into Unity is Unity being a game engine, one of the core components of a game engine, which are effectively physics engines, is this thing called the game loop. Okay. You can think of it as basically a thread that runs every single frame. So there's something that's running in the background every single frame. So by learning about threads first, we now have this concept of having stuff that's happening behind the scenes that doesn't prevent the next thing on the screen from happening, non-blocking code. So a thread is very much a part of every single game you make in Unity. Now we know what threads are. We'll talk a little bit about how threads talk to each other to wrap this up, which is going to be very similar to how processes talk to each other. And then we'll jump into Unity. If you wanted to, I don't know if you'll necessarily need it for next class, but I have a link up on Blackboard to Unity. You can go and download it and get the latest, greatest released version. Don't look at it. Don't do any of the beta ones. You'd probably be fine even if you did, but whatever the latest released supported version is of Unity, go ahead and download that, get everything installed on your computer, because that could take some time. All right. I will see everybody on Friday. Remember, it's Zoom only on Friday.